case of the steam sawmill, the shafting and counter-shafting needed to drive the machines imposed severe limitations on the scope of plant layout and formed an obstacle to planned workflow, so each machine came to be treated as a unit on its own. Thus, the pattern of woodworking practice was evolved. Almost without exception, a series of progressive machining operations, one following the other with intermediate resting places for timbers between operations, became the accepted production method. Whilst this system required a large labour force, labour was, at that time, cheap and in plentiful supply, but now the situation has completely reversed. In present-day trading conditions, the cost of the final product has a vital bearing on sales, and it is imperative to reduce costs to the lowest possible figure. The biggest single item is the cost of handling, which in certain sections of the industry has been successfully reduced by mechanical aids such as forklift trucks, side loaders and the like. In joinery production, these aids do not entirely solve the problem due to the infinite variety of loads and restrictions in work area, and the cost of handling has been steadily rising. Whilst machines themselves have evolved into extremely efficient units, the feeding and performance of some hand-operated machines, in particular the crosscut saw, has been neglected. The measure of efficiency is the ratio between the actual cutting time and the time taken handling the timber. The latter includes taking the timber off the stack and placing it in position for cutting and re-stacking. To the casual observer, a crosscut saw appears to be operated in a reasonably efficient manner, but when the operation is analysed, it becomes obvious that appearances can be deceptive. Here we see how the operation of a manual crosscut saw is analysed. The clock indicates the time taken in seconds. These two columns will indicate the actions of the operator and crosscut saw respectively. This is the key to the actions referred to. The darker shading represents the time taken to remove the cut piece and to place the next length against the stock. The lighter shading represents the actual cross-cutting operation in both columns. The lighter stripes represent the time taken to remove the offcut, and the darker stripes represent the placing of the next length of timber on the table. The findings of the bar charts are summarised in these two columns and show the actual utilisation of the operator and cross-cutting machine. From this summary, it becomes obvious that the saw is working usefully only a fraction of the time. With an efficient team, as assumed for this analysis, only about 20% of the operator's time is spent actually cutting, though more often this figure is much lower. The remainder of the time is handling time, during which the crosscut saw is, of course, idle. Here is the complete analysis, from which can be seen that the machine is cross-cutting only a small portion of the total working time. As already shown, the operation requires a three-man team, only one of whom is actively engaged in cross-cutting, and then only less than 20% of his time. Because there are 3 men involved, this nominal 20% equals less than 7% of the man-hours shown, an extremely low efficiency rating indeed. It is obvious from this summary that in order to improve production appreciably, it is necessary to make inroads into the balance of the operational cycle, i.e. the handling time. In almost every joinery mill, there exists a primary production line irrespective of the end product. In most cases, it is not a production line as such, but merely a general pattern of workflow from the mill entrance through, perhaps, 2 or 3 crosscuts, and then into a moulder for moulding or primary sizing. Between processes, the timber is invariably handled manually, with a delay between operations. The conventional mill is certainly a hive of industry, but as we have seen from the analysis, a very inefficient hive indeed. But with the introduction of mechanical handling equipment, efficiency is improved considerably. And this is what has been achieved so successfully with the Robinson-Buckley automated crosscut line. The crosscut operator of such a line is relieved of 90% of the physical handling of the boards and is thus able to concentrate purely on selection and crosscutting. A travelling tilt hoist unloads a timber set from a truck and discharges the timbers layer by layer onto a transverse conveyor, which drops them one by one onto the crosscut infeed table. The crosscut is hydraulically operated and the tables are live, with rollers on the right-hand infeed table and an endless belt on the left-hand outfeed table. Up to 8 or 16 length gauging stops are provided, and these are selected by the operator moving a handle in a notched quadrant. Because of the high degree of mechanization, the operator is able to crosscut at approximately 3 times the rate of his counterpart on the manual crosscut. In addition, only one man is required to operate the crosscut, thus cutting the labour force by 2/3. Here we see how the operation is analysed. As indicated by the key, the dark shading represents the placing of the timbers against the stops, which is done automatically by the powered tables under the control of the operator. The lighter shading represents the actual cross-cutting operation. The dark stripes represent the placing of the timbers on the infeed table from the tilt hoist via the cross conveyor. Removal of the cut pieces does not figure on this chart, as this is automatic. In the diagram, the cut pieces are shown as dropping onto a pallet. In practice, of course, they continue onto a second conveyor. Again, the findings of the bar charts are summarised in these 2 columns. They show a considerably increased percentage of cutting time and a correspondingly reduced percentage of handling time. Hence, output is greater. With the automated crosscut, 30 pieces are produced in 1 minute by 1 man, as compared with only 10 pieces per minute produced by a 3-man team on a manually operated crosscut. In terms of man-hours, this represents 1,800 pieces per man-hour on the automated crosscut, as compared with only 200 pieces per man-hour on a manually operated crosscut. Here we again see the mill with the manually operated crosscuts, which, because of their high labour requirements and extreme slowness of operation, is very inefficient. General studies revealed that 3 manually operated crosscuts are needed to serve 1 moulder operating in the normal feed speed range of between 40 and 60 feet per minute. As proved by our analysis and confirmed in practice, a single automatic crosscut can replace 3 manual crosscuts and maintain the same production. It only then remains to connect the crosscut to the moulder in such a way that a continuous feed is maintained to the latter, even though the output of the crosscut is, perforce, intermittent. This is achieved by installing a fairly long series of conveyors to carry a buffer stock, i.e. a temporary running storage. The last conveyor immediately in front of the moulder has booster rollers to bring the timbers up to the fence and force their entrance into the machine. Hence the operator is released for other work. As transfer between crosscut and moulder is automatic, the only trucks now needed are those feeding the hoist and taking off the moulder. We can now appreciate the vast difference between the operation of the automated plant shown here and the conventional plant shown earlier. Whilst the primary aim of factory mechanisation is lowering of costs, in addition, production is streamlined and internal transport becomes a minor problem. Planning becomes simplified and buffer stocks are reduced to an absolute minimum. From this plant, staffed by only 2 men operating an automated crosscut and moulder, exactly the same production can be achieved as would otherwise require 11 men operating 3 manual crosscuts and a moulder. This is the efficiency that automation brings. But so much for facts and figures. Now to show you the machine actually in operation. Timber is brought to the crosscut on yard bogies. The truck may be loaded at the outfeed end of a machine preceding the crosscut in the production line, such as the resaw shown here, or in the mill yard, where a certain amount of pre-selection will take place. The bogie is then brought to the correct position relative to the tilt hoist, where it can be left until required. With the exception of the moulder, all the transfer equipment is under the control of the crosscut operator. The conveyors beyond the crosscut outfeed table run continuously and are the first to be started. Next, the crosscut saw is started and the action checked. The machine completes the full stroke only when the foot pedal is depressed and